All right. Today's topic of discussion is gas hydrates. Give me one moment. Let me switch on my. Okay. So are my slides visible to you? Can you see it properly? And can you hear me all right? Can someone just confirm?
Yes, sir.
Yes, sir.
Yes, sir.
Very good. Okay. So today we are going to discuss about gas hydrates. So gas hydrates have different names. I don't know if you are familiar with gas hydrates, whether you have heard about this particular type of fuel before. But if not, we are going to discuss it today. Okay. So it has different names. They are called clathrate hydrates. They are also called gas clathrates, gas hydrates, clathrates, hydrates. All these are different names, but they refer to the same thing. Okay. What are they? They are crystalline water-based solids physically resembling ice, in which small non-polar molecules, typically gases, are trapped inside cages of hydrogen bonds and hydrogen bonded frozen water molecule. So, in a sense, what we essentially observe, the deep within the ocean, there are, chunks of ice, okay, like you see here, chunks of ice, nothing but the normal ice, and those ice actually trap a lot of hydrocarbon in form of gas. Okay, it has a lot of trapped hydrocarbon in terms of gas in the gaseous form in this ice which actually form deep within the uh, ocean floor. Okay, and the we will see about how much there is in the earth and everything, but just as a starter we can say that it is almost, I mean, if you think about the total oil and gas reserves of the world, it's almost, no one knows how much, almost 10 to 100 times more than whatever reserve we have. Okay, so the next question that will come to your mind, that if you have so much of gas trapped in such ices, why can't we explore them? Why can't we have used them so far? And that there are some technical challenges to exploit this sort of gas hydrates, which is entrapped in such ice, and we will discuss them. What are the challenges? And because of their technical challenges, it's uh, still quite demanding. I mean, how to actually get the gas out from these ice? What are the challenges? We will discuss. So far, there is only one demonstration project happening in Japan, where people could, showed that they could take out gas from these clathrates. Okay. Now, of course, it is a proven fact that there is gas. Everyone knows that there is gas in this ice, but then people do not know how to take them out. Okay. So that's all about the clathrates. That is what we are going to look at today. Okay, so this is a typical crystal structure of ice. Okay, so gas molecules, and you can see here the gas molecules are kind of entrapped, right, within the ice structure. Okay. So the idea is, if you break the ice structure in a way, okay, you have to break the ice structure in a way so that you give a pathway for the gas to come out. Okay. That's the overall philosophy of the whole thing. Okay, so the gas molecules are encaged between ice lattices. So the in the ratio of 85 to 15. So if there is 85% of water, then there is 15% of gas molecule. Okay. Now, if you see the amount of ice which is under the ocean floor, okay, you will be amazed what that means in terms of it is if 85 to 15 ratio, how much gas we are talking about. It's really too much. So contains 160 to 180 times natural gas by volume at standard conditions. Okay. So this is entrapped. So entrapped means it is highly pressurized. Okay. So these gallium gas molecules are highly pressurized. But when you take them in the room temperature, in the room pressure condition, what it means in the atmospheric pressure condition, it will expand 160 to 180 times. Okay. So there is a lot of gas. The moral of the story is there is a lot of gas which is entrapped in these clathrates. Okay. The only thing is we have to be able to take them out. So these are some of the pictures. So this is such ice which has been taken out or dredged from the sea floor. Okay, these are some of the pictures of such ice. Okay. Here you can see within the rock the ice is kind of entrapped. Okay. This is someone is holding such ice, and if you fire it, this ice will burn like a magic. So such ice, why do they burn? Or you can put them into flame. You never can put ice into flame simply because they have entrapped uh, hydrocarbon in them. Okay, so they form. What are the different forms? They can form nodules, like we can see here, like small pebbles. We call them nodules. Like perhaps you have heard about manganese nodules. Similarly, they are like ice nodules within which like small conglomerates, small balls of ice in which the clathrate can stay. It can be as lamina, like you can see here, small laminar stuff, and it can also be as veins. It can stay as vein in them. So nodules, lamina, and vein, these are the general forms of naturally occurring ice in the sea floor within which such gas can be stored. So here we are looking at the types of gas hydrate deposits. Okay. So although all factors controlling the type, distribution, and amount of natural hydrates accumulations are poorly understood. Okay. So it's still not something people know a lot like they know about, say, coal or natural gas or oil. This is still under research. Okay. Geologic environment is known to play a significant role. Okay. So you need actually good geologists to help engineers to exploit this wonderful resource, which is kind of still unexplored. Okay. In particular, gas hydrate formation is influenced by the porosity, permeability, and degree of lithification of the enclosing medium. Okay, so such ice you will generally find there is a small, there is a layer of mud. Within the layer of mud, there is such ice accumulation. Okay, and in such ice, of course, you will have the presence of such gas molecules. Okay, and the porosity and permeability of this overlying horizon, like which forms like a seal, which forms is not typically a seal, but the mechanism is very similar. The porosity of permeability of this overlying medium is very important. So where do you see gas hydrates to be present? Okay. So the hydrate stability zone ranges vertically between 1,000 to 2,000 feet. Okay, and cover a large horizontal area. Okay, so from the surface, so from the sea floor, you have to go around 1,000 to 2,004 feet below the water to actually find such gas hydrates. If they are shallower, what essentially happens that the gas hydrates do not stay within the ice crystal. Okay, they escape automatically, naturally. So the ice crystals, you will find ice, but you will not find ice which is rich in methane. Okay, or which is rich in the natural gases, hydrocarbon gases, right? So you have to have a depth window of around 1,000 to 2,000 feet, right? So you have to go, depth greater than 1,500 feet, okay? And then solid methane hydrate ice forms in bands and lenses close to the surface, okay? So, like, it might not always be under the sea. It can be like the Arctic in the permafrost deposit. Okay? In the Arctic, in the permafrost deposit, you will find such clathrates immediately beneath the surface of such, in the Arctic or in the permafrost region. You will find solid methane hydrates in ice forms as bands. Okay, like you can see here. Okay, or lenses close to the surface, and so how this methane comes, the methane is essentially not produced here. The methane is still produced in a source rock, like a typical hydrocarbon source rock, right? So for example, I have a shell here, okay, that will actually expel hydrocarbon, but the hydrocarbon will slowly seep through the media and then get trapped within this ice. Okay? So it's like it is not getting trapped in a reservoir, rather it is getting trapped in a within the ice. Okay, but then also biogenic gases, that also, at least in these shallower intervals, the biogenic gases also play significant role in enriching the clathrate deposits. Okay. Similarly, you can have impermeable solid methane hydrate embedded in mud. Okay, so like you can see here, that like the example that we have given, like there is a mud, and then below the mud there could also be a ice layer where the gas could be trapped, where the thermogenic gas is actually enriching this particular deposit. Okay. So if I want to put it in a nutshell, you can find it in a little in the shallower region, immediately below the Arctic or Antarctic area where there is permafrost present. Okay, below permafrost, that could be shallower, as well as maybe little bit, just under the ground where there are ice layers, which could have fed by the biogenic as well as thermogenic gas, and then you can find them under the sea. Okay, beneath the impermeable mud layers. Okay, so here is the here are the areas where you can find gas hydrates. You can see it's you have to remember about the depth, of course. So in the depth window, you can find gas hydrates almost everywhere. Almost every shore of the world, you have huge potential of gas hydrates. So the red dots actually indicates gas hydrates inferred, that people, scientists have said that there could be gas hydrates here, and the blue dots indicate that the gas hydrates recovered, that people have, you know, not commercially. I'm not saying that they have done commercially, but they have gone out, dredged the ice out, and saw that there is gas inside. Okay, look at India. Okay, there is very big potential, because India is like a semi island, right? Three sides of India is like covered with sea, and then so as a result, all the shoreline of India, both in the east coast and west coast, have enough potential for gas hydrates and clathrates. Okay, So is in Africa, so is in America, almost everywhere. Wherever there is a boundary with the sea, there is a shoreline. You can have the possibility of gas hydrates, and people have proved and inferred worldwide. So the moral of the story is the reserve is exponentially huge. Okay, huge. It's a lot and lot and lot of gas just waiting for the right technology to be taken out of the ground. Okay. So it's the ice that doesn't melt. So it is formed at low temperature, but at high pressure. You need high pressure to actually hold that gas molecules inside the ice structure, known to occur at temperature below 295 K and a pressure greater than 3000 kPa. Water molecules attach themselves through hydrogen bonding and form cavities which are occupied by a single gas or volatile liquid molecule. Gas or volatile liquid inside the water cage stabilizes the structure through physical bonding via weak van der Waals forces. Okay? So that is the way, that is the mechanics by which the gas molecules attach themselves with the ice structure. So this is the worldwide reserve. If you want to have a look, okay, uh, and you can see their relative scale of reserve with respect to different countries, right? India is also holds a significant place. But the larger the shoreline, of course, you have higher amount of reserve. Okay, so hence you can see the Arctic Ocean. Of course, the oceans have very very high clathrate deposits. So how much is total? By the way, the ones that I have, the scale for this one was sorry. These are expressed in TCFs, okay? Trillion cubic feet. The numbers are expressed in TCF, trillion cubic feet. So in total, 700,000 TCF, 20,000 trillion cubic meter of clathrates waiting to be explored. Conventionally recoverable methane is only 8,800 TCF. Yeah. So, like the ones that we have been discussing so far for last 3 months, that only covers for 8,800 TCF. But clathrates only, you can now see the scale, 700,000. This is for clathrates, and conventional methane, conventional gas, 8,800. Okay, you can do the math. 7,000 by 88. How much is it? You can do the math. Uh, how many times of hydrocarbon is present in these clathrates? So 2 times the total energy in coal. If you now include coal, oil, and conventional gases, everything together, the total energy, whatever is stored in clathrates, is already 2 times more than all the coal, oil, and gas, whatever is present and whatever have been exploited so far by human being. Okay, so it's really, really, really huge. So if you can unlock these clathrates, I mean, you will almost get a Nobel Prize. It's such an important deposit, and people don't know how to take them out. So it's a future source. We will see what sort of climate change challenges that this can bring about. We'll see in a moment. It affects sediment strength. which can initiate landslide, slope, and which can initiate landslides on the slope and rise. Okay. So what do I mean by that? Because here in this particular case, you are actually, so say for example, this is the coast of India, and there is this huge chunk of ice sitting here, right? Huge chunk of ice sitting here, and that has a considerable mass. Now, if you want to take out clathrates from this, you have to remove the mass from here. Now, if you remove such a huge amount of mass from a particular place, what people have not done historically, okay, people have made mines, have built roads, but here we are talking about a very different sort of scale. The scale is entirely different. Okay. So if you remove that mass, people don't exactly know what that would bring about, whether it will trigger earthquakes, whether it will trigger landslides. There will be, of course, a lot of land instabilities associated with taking the keys, taking such huge mass out of the ground. If you take that huge mass out of the ground, there must be some instabilities which would be expressed by landslides, who knows, subsidence, earthquakes, who knows. So there is a huge risk associated with that. And people exactly don't know what exactly is what exactly is the magnitude of that risk. So methane from hydrate reservoir might significantly modify the global greenhouse because methane is 20 times as effective greenhouse gas as a carbon dioxide. And gas hydrates may contain 3 order of magnitude more methane than exists in the present day atmosphere. So the challenge is, say for example, if by some because this is not entrapped within the so the advantage for conventional oil and gas is that there is like a huge cover of overburden, and then there is your reservoir, right? So you are like drilling small holes, you are poking through it, and you are taking your oil and gas out. So there is no chance that all the gas and oil will all on a sudden kind of explode and be released in the atmosphere. Okay. That chance is not there. But then for clathrate, that chance is. Now you know that methane is also a greenhouse gas. Now, what would happen if you, by chance, by mistake, if you can't handle it properly, if you can't take the methane out in a controlled way, if there is an uncontrolled explosion of methane gas all around, what would happen? If there is no fire, if we take out the fire question out of the box, maybe we say for the sake of argument there is no fire. If that methane gas is released in the atmosphere, okay, forget about its toxicity and everything. It will change the complete scenario of the global greenhouse because methane is almost 20 times as effective greenhouse as than carbon dioxide. So there is this huge, because their natural occurrence is such that it is very difficult to exploit clathrates in a controlled way. And if there is an accident associated with the release of clathrates, the methane gas that you want to take out, it will be completely uncontrollable. Here, for conventional oil and gas, it is controllable because it is covered under overburden. Okay? Gas hydrates apparently cements sediment. Okay? Therefore, it can have a significant effect on sediment strength. Its formation and breakdown may influence the occurrence of local submarines and landslides, which we just said. Okay, it's like this mass is kind of cementing the whole sediment of the seafloor together, right? This ice. Okay, and if you remove them, if there is a mass imbalance, people don't exactly know what mechanical instability it will bring about. It can give rise to earthquakes, it can give rise to submarine landslides, and so on and so forth. Okay, hang on. Now, on the other hand, methane is an environmentally cleaner fuel than oil, coal, or oil shell, which all have immense environmental impact during production and consumption. Now, of course, if you can take the methane out, that will be advantageous, because if you burn methane, the amount of carbon dioxide which is released by, by methane is not significant. Okay, so the greenhouse gas emission will be less. So it's the best possible fossil fuel in terms of the its adverse effect of polluting the atmosphere. Okay, so in that way it can be good. So what are the proposed present day techniques by which you can pick out the cathrates? One is thermal injection. Okay. Unavoidable heat losses due to host rock economical infeasibility. So this is the challenge associated with thermal injection. Thermal injection means you essentially pump some sort of hot fluid into the water, okay, and then wait for the ice to melt, and you say that the gas will come out. But then what is unavoidable is the heat loss due to host rock, and it actually costs a lot. Depressurization, that you kind of take the clathrate out and depressurize it, the pressure is released, and then that would release the methane. But the challenge is endothermic nature, causing decrease in reservoir temperature. Okay, so if you depressurize, the temperature will also decrease. Okay, so it will also kind of again increase the stability of the methane. So inhibitors, methanol and ethylene glycol are expensive chemicals, and then there is something called inhibitors. You put some sort of chemicals inside, like methanol or ethylene glycol, that would also help you to release the methane. But then they are expensive chemicals. So there are three processes by which are proposed to take the cathrates out: thermal injection, depressurization, and inhibitors. And all of them have their own challenges. Okay. Now, nowadays, with advancement of technology, new microwave technology is proposed, like laser. Put kind of lasers on the clathrates and hope that will melt your ice. Yeah. So it's not. So this kind of explains you what essentially is happening around. Okay, so you can see here that the thermogenic oil and gas is actually, for example, here I have source rock where it is generated, and then this is moving up. This is the migration that we have talked about. If there is fault and fracture plane, it moves quickly. Okay. Then it finds a oil and gas reservoir, the conventional oil and gas reservoir. And then if that is leaked, that can also leak out. If there is a fractured system, that can leak out and kind of get released in the atmosphere through the ocean. But then of course, if that hits an ice, that would create gas hydrate, be it at the surface or at some depth. Okay. Similarly, you can have biogenic gases. Okay, biogenic gases can also, trap them within the ice. Okay. By microorganisms, CO2 plus H2O. That sort of reaction that happens is equal to CH4 plus CHO. So CH4 is released because of the microorganism, mostly bacteria. That can also release the biogenic gases, which gets trapped inside the clathrates. Okay, and then of course through mud volcanoes, gas always do escape in the atmosphere. So what are the general takeaway points? So huge amount of natural gas trapped in hydrates, too enormous to ignore. It's really, really large. It's a threat to climate as well as it's a threat to climate as well. So there is an urgent need that we use it for positive purposes. Technology and scientific understanding for exploitation of gas hydrate is to be developed. Much of the learned, much to be learned before gas hydrates can be considered as a resource. The integration of various science using the fluorine technique will play definitely a vital role in methane extraction. You can read about what fluorine technique is in the internet, which is generally is kind of the future for exploiting gas hydrates. Okay, so that's all I wanted to talk around gas hydrates. If you have a question, please ask. Yeah, any questions, guys? Let me see. Aniket, any questions from you? Did you understand about clathrates?
Yes, sir. It was okay, sir.
Did you find it interesting?
Yes, sir.
Have you heard about clathrates before or not?
Sir, yes, like when you taught us about in the first year, sir, little bit that time.
Okay, 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 okay.
Yes, sir.
Meenakshi, do you have any question? Nadeem, Niraj, Nirul, Pratichi, anyone, any questions, any comments? Okay. If not, I wish you all the best. And yeah, I will see you in future in the class. But then, of course, today I will, in a moment, maybe in 10 minutes, you will find your quiz questions. And yeah, all the best for your end sem exams. Thank you.